Good morning. All right. And now it's 11:30. Alrighty, I will try and still got 30 minutes of morning. All right, so um, just a brief overview about what we're going to do today so we can jump right into it. So I do have about 20-30 minutes worth of example that I want to go through. There's the last example number 3 that you should see on your page, and then there's an application that we're about to talk about. So just as a preview to that application, I don't really care if you understand the application. I do care that you understand the calculations that go behind the application. So I'll try and very briefly go over the application. For those of you who I'm sure are thinking, well, why are we doing it if he doesn't expect us to know it? Is because I want you to see that what we're going to do has applications, even if we're not testing said applications. So, to answer the question that nobody really asked. So that's my plan for today. So just those 2 examples. And then the rest of today is just for me to answer any questions that you have with regards to the mathematics or with regards to the final exam. Unfortunately, I can't answer everything. Because the final exam isn't made up completely yet, but I will do my best to answer that. But first, I want to go through the examples. So before people start firing off final exam questions, just hold off on it. I want to get through the rest of the material, and then you can hit me with your best questions that come after that. So that's the plan for today. In terms of announcements, I'd really like general announcements that I normally start with. I really don't have any because the course is pretty much done. We are working our best through to try and get those tests marked. My plan is to return the test. So for Friday tutorials, usually you get your tests back on Friday. For Monday tutorials, usually you don't. So my plan is, although I hope the other instructors don't have an issue with this, my plan is to send everything back tomorrow. So tomorrow is the VW deadline because weird things happen when there's strikes. But tomorrow's the VW deadline, so I can't guarantee that everyone's going to get their test 5 back. That being said, you have 4 tests and a midterm, so you should probably know where you stand even without the 5th one. But for those of you who either want it for studying purposes, for obviously that's great, or to make a decision, I am going to send back your tests even if they're not marked yet. Or I shouldn't say that, even if they're not completely marked yet, every test has some of the questions marked. But if you get your test sent back to you, make note of your group number because I'm going to be saying which groups don't have it marked yet, and just say, all right, if question 3 isn't marked, it's not because we forgot, it's because it's just not done yet. So that is my plan in regards to test 5. So you are going to get it back, but some questions I can't guarantee are completely marked yet, especially if you're in a Monday class. All right. But other than final exam questions that I'm going to hold off for about 20-25 minutes, any questions about any of the rest of it? Said a lot of things fast there. Beautiful. All right. So questions 1 and 2, we finished on Tuesday. So I'm going to give you a few minutes to give question number 3 a try to see if you can figure out how to diagonalize that 2x2 matrix 5, 2, negative 2, 1. I think we did, unless I'm mixing up my 2 classes. Yeah, we finished question 2. A04, yeah. Yeah, so for question 2, we had eigenvalues 3 with multiplicity 2 and 4. And then when we created P, we just came up with 2 eigenvectors for question number 2. But we were kind of specific about how we created them because they came from our eigenspace for 3 that had 2 parameters in it. And we got one of the vectors by letting one of the parameters be 0 and the other 1, and vice versa for the other one. So we had to be a little bit more careful how we made those eigenvectors because we couldn't have those vectors being linear combinations of each other. All right, and you're probably not all the way through, but just hopefully you've had enough chance to at least think about it, maybe get started on this question number 3. So let's talk about, so what's the first step? We want to diagonalize this matrix, or at least see if it is diagonalizable. What's step number 1? Find the eigenvalues. Beautiful. Call this thing A. Lambda I minus A. Its determinant is equal to 0. Start the solution. That's lambda minus 5. I have not been good with my lambdas lately. Lambda minus 5, negative 2, positive 2, lambda minus 1. It's 2 by 2, and so it's just a 2 by 2 determinant. So it's that lambda squared minus 6 lambda. I'd like to see it. Gives us an excuse to give part marks for stuff. What's the 0 mean? 0 equals the determinant. The left-hand side of the equation. I kind of got a little squishy because I wrote it in the wrong way. All right, so little 2 by 2 determinant. Certainly not as crazy as some of the 3 by 3s we've seen. All right, so what are our eigenvalues? Yeah, 3 twice is a weird but perfect way to say it. We factor this thing, it's lambda is equal to 3, and so we get lambda equals 3 with multiplicity 2. So lambda is equal 3 with what we really call algebraic multiplicity 2 because it comes from the algebra. Kind of implies there will be a second one. We call that foreshadowing. All right, so we got one eigenvalue. It did have multiplicity, but we got one eigenvalue, lambda equals 3. Beautiful first step for diagonalizing. What is our second step? Find the eigenspace. Beautiful. Lambda is equal to 3. Shove it into here. Set it equal to 0. We get negative 2, negative 2, 2, and 2. Depends on how the question is phrased. If the question is just find the eigenvalues, no. The question says find the eigenvalues with multiplicity, yes. It's going to be useful here because that multiplicity thing is going to be important in terms of what we're doing. So I always write it because it's important for what we're doing. So I would suggest doing it. That being said, as always, answer the question asked. All right, so row 1. Again, we've row reduced a million things at this point, so I won't focus too much on the row reduction. Minus 2 row 1, and we get 1, 1, 0, 0. As always, we get at least one row of zeros, or else we either made a mistake row reducing, or our value wasn't actually an eigenvalue. All right, so here is our reduced row echelon form. So what is our eigenvectors? How do we find our eigenvectors? How do we find our eigenspace? That's certainly the answer. How do we get that? Sure. We get careful here, we have a column without a leading one. There is a 1 there, but it's not a leading one. So whether you call it y, I'll stay consistent with my x1, x2, but there's nothing wrong with doing x and y. And then x1 plus x2 equals 0 tells us that x1 equals negative t. Some people said t and then negative t. That's also correct. And our eigenspace is the set of all vectors negative t, where t is some real number. And again, if you had t negative t, it's the exact same thing. That's also fine. I mean, it isn't the exact strategy we used from chapter 1, but the x1 could be t and x2 would be minus x1 either way. All right, beautiful. So that says D. Well, we had 3 with multiplicity 2. So what's P? So P is our matrix with eigenvectors. So we need 2 eigenvectors in order to get our 2 columns for P. What are our eigenvectors? And again, as always, there's usually more than one correct answer. So negative 1, 1, beautiful. That's just plugging in t equals 1 into here. What do we get for a second column? Negative 1, the same one twice? Okay. All right, so we can get the same one twice, or we could get different eigenvectors. Is this an acceptable matrix P? Is this an acceptable matrix P? No, why not? Because the determinant is 0, it's not invertible. All right, well, that obviously, okay. So in general, picking the same eigenvector twice is never going to work out well. So let's get a different eigenvector. What's a different eigenvector that we can put in there? T equals 0, 0, 0. I mean, technically, that's not an eigenvector. Negative 2, 2. All right. Does negative 2, 2 work? No. No. Why not? The determinant's still equal to 0. All right. Any other ideas? Yeah, it's always going to fail. Why is it always going to fail? Repeating's not exactly the word we're looking for. Why does this fail? Not the final conclusion. We'll come to the final conclusion. Right, because they are always multiples of each other. They have to be multiples. Why do these have to be multiples, but we didn't before? In our last time we had multiplicity 2, they weren't multiples of each other. And scroll up. Bang. Right here. Specifically, what about the eigenspace made the last one okay and this one fail? I'll even scroll up to the eigenspace. Here was our eigenspace for the eigenvalue of multiplicity 2. So in our last example, we had 2 free variables. We had 2 parameters. Since we had 2 parameters, we could get 2 eigenvectors that were not linear combinations of each other, or in this case, multiples. Right? We had 2 different parameters, so we could get those 2. In this case, how many parameters did our eigenspace have? Just 1. So, this is not diagonalizable. And the general idea is that A is diagonalizable if the multiplicity is equal to the number of parameters in the eigenspace. We actually give this, you don't need to know this word, but this does have a name. It's called the geometric multiplicity. Well, the previous 2 by 2, we had two different eigenvalues. So for the previous 2 by 2, we had two different eigenvalues. So each eigenvalue had multiplicity 1. So technically, this rule comes into effect because we had eigenvalues of multiplicity 1, and we were able to get one eigenvector, because we always get at least one parameter. The question is, if the multiplicity is more than 1, then let's say if the multiplicity is 3, then we would need 3 parameters. If we don't get 3 parameters, then we get a problem. Yeah, and so here's where we're getting into theory that's a little bit beyond, unfortunately, we have time to cover in this class, and it involves some of the chapter 2 stuff. But the number of parameters will never be more. And I'm not saying that's an obvious statement, but the number of parameters will never be more than the multiplicity. It's just impossible. I can't prove that to you with the knowledge we have in this class. It involves the chapter 4 stuff. So for those of you who have the full version of the text, feel free to read through the chapter 4 stuff, which gets into that a little bit more. But that's just not possible. And secondly, we always have to make sure the columns match up. So even if it was possible, then we always have to have the eigenvalues corresponding to the eigenvectors. So it wouldn't work anyway. So yeah, so I'm not saying this is a proof. I'm giving you a statement without proof. I'm not saying this is obvious, but this is something that's true. So if you ever get a multiplicity of 3, but only 2 parameters, then it won't diagonalize. It doesn't happen a lot, but as we see in this example, it can happen. All right. So any questions about this example? All right, so I am going to talk very briefly about an application of this, of why we would want to diagonalize a matrix. Why is it so special? So what was something we talked about in chapter 1? We did a specific example, and I said, man, this is awful for general matrices, but for diagonal matrices, it's very easy. So let's say if, and we know it's an if. We definitely know that this is an if. If A is diagonalizable, in other words, if A can be written as PD P inverse, I haven't gotten to the slide yet. I'm just kind of explaining something first. I'll come back to the slide. We finished off the slide. So the question is, what is A squared? So if A is equal to PD P inverse, what is A squared? Where are we getting that from? That's absolutely true. PD squared P inverse, but why? Why isn't this P squared D squared P inverse squared? Yeah, because we can't really do that. As weird as this might seem, but this was all in our everything that fails with matrix multiplication, is if you're squaring a product, then you can't square them individually. That's just not something that's usually true. So that's wrong. So as some people mentioned, A squared is A times A. So that's PD P inverse, PD P inverse. Now again, Why can't we just go P cancels with P inverse, P cancels with P inverse, and get D squared? Or maybe we can. But I probably phrased it in my way. Yeah. Because, yeah, they only cancel if, as somebody said, perfect answer, they only cancel if they're next to each other because you can't change the order. So a couple of these do cancel, but not quite as many as we'd like. Which two cancel? Right, the middle ones, because what is P inverse times P? Yeah, that's equal to I times D times P inverse. So multiplying by I doesn't matter, and so we're left with D squared P inverse, as somebody mentioned, and that's the exact correct answer. Of course, you're never going to square a matrix by, all right, let's find the eigenvalues, let's find the eigenvectors, let's create P, let's create D, let's find P inverse, and square a matrix that way is obviously overkill. Probably overkill for A cubed, but what happens when we do A cubed? Stuff to it, yeah. So that's going to be PD P inverse, PD P inverse, PD and P inverse. So 3 A's multiplied. There's I. There's I. And so it's P DI DI P inverse. Forgot a D. So P D cubed P inverse. Again, complete overkill for cubing a matrix. You would never do this to cube a matrix. But if I say A to the 2021, now all of a sudden multiplying A 2021 times, well, what's that going to be? What's A to the 2021? Or in general, just for any n? D to the 2021 P inverse. And while it might have been overkill to do this for A squared and A cubed, heck, even A to the 4, A to the 5, it's going to be a lot less time just to multiply the matrix A that many times. When you start getting to 10, 100, 1,000, now all of a sudden you're saving time by diagonalizing. All right. So, again, might seem like, all right, well, that's great, but why do we care about taking powers of A? And that's going to bring us to our next example. So I don't care if you understand. I mean, I'd like you to understand. I guess I shouldn't say I don't care. It's not required for you to understand the application, but I want to do this in order to give you some reason why these kind of techniques can be useful for us. All right, so here's the application. Suppose Shaw and Bell MTS start with 1,000 customers each. After each month, 10% of Shaw's customers move to Bell, and 20% of Bell's customers move to Shaw. After a very long time, how many customers does each have? And there's a lot of assumptions here. These 2,000 people, I guess I gave that away. These 2,000 people will never leave. It's like Hotel California. Once you get in, you can never leave. So you... and nobody's entering the system. I'm not saying you can't handle that. I'm not saying you can't handle that situation. I'm just trying to keep the application as simple as possible because my focus is on how to take the large powers. So I expect you to know how to take the large powers. That is one of the learning outcomes here, is that if I give you a matrix, that you be able to do A to the power of 15 million, that you can do that. I just want to do it in the context of this application, so the application part I'm not overly concerned about. All right, so that being said, I am going to briefly talk about the application just to give you some context, but I will tell you if you want to tune out because I said words like this thing you didn't need to know, I will let you know when you have to tune back in order to have something that I expect the knowledge for. All right, anyway, so I'm going to create a matrix. We're going to create a vector because apparently this is linear algebra. So I'm going to let Bn stand for the number of customers Bell MTS has, Sn be the number of customers Shaw has, and I'm going to let the vector An be Bn Sn. So what is the vector A0? So the vector A0 is B0, S0. Now, I don't want the numerical answer. Not that I have a problem with people giving it. So I don't want the numerical answer to this. I want, what does B0 stand for? So what is B0 standing for? AN is BN SN. Right. No, it's not when Bell has 0 customers. What is N in our, what is N standing for here? Before I get to what BN, yeah, N is standing for the number of months. So B0 is talking about how many customers Bell has at 0 months. In other words, how many they start with. So B0 is how many Bell starts with. S0 is how much Shaw starts with. And how many do they each start with? In this example, how many do each start with? 1,000. All right. So for those of you who have used the word or heard the word recursive, this is about a recursive thing, right? We're going to have what we start with, and then we're going to, each month, we're going to have some kind of recursive process. So if that's a word that makes sense to you, then great. I was thinking more computer science, but stats has a part of it as well. If that word has meaning to you, great. If it doesn't, I don't care. We're not doing that part. All right. So the question is, what is A1? So how do we find out how many customers Bell has after 1 month? So let's go back to the page here. So how many customers is Bell going to have after 1 month? How do we compute that? And again, if you don't understand this part of the application, that's not my concern. But I'd like when students answer questions. So, as you guys have figured out over the last 3 months. How can we tell? So, I mean, we're not increasing their customers by 10%. There's nothing here that says Bell's customers increased by 10%. What is 10%? Sorry, let me rephrase that. 10% of what? Yeah. So we take how many Shaw had, take 10% of that, and add that to Bell. So we're going to get 10% of Shaw. So S0. But Bell loses customers too. So we want, as somebody said, we're going to deduct, I miss when they were just MTS, but we're going to deduct 20%. So how much do they keep? So this 10% is how much they gain. We also need how much they have kept of their original amount. So if we lose 20%, what percent do we keep? We're keeping 80%. So we get 80% of B0 plus 10% of S0. That's how much Bell is going to have after 1. Again, if that's a bit confusing, don't worry too much about it. Again, I just want to give a brief overview of the application. What about S1? How many is Shaw going to have after that first month? Not the numerical answer, but how we find it, because it's how we find it that's important here. So how many of B0 does Shaw get? So we're going to get 20% of Bell. B0, and we're not losing, I mean, we are losing 10%, but again, we're talking about how many Shaw is going to have, not how many Shaw is going to lose. So how much is Shaw going to have? All right, 90% of S0. In other words, 0.8 B0 plus 0.1 S0, 0.2 B0 plus 0.9 S0. And we can write that as matrix multiplication. Again, not saying this is necessarily obvious, but we can write this as 0.8, 0.1, 0.2, and 0.9. Just as matrix multiplication. All right, so this is how we could compute A1. Seems a little bit convoluted. Notice how I'm not putting 1,000 in. Of course, you could put 1,000 in, but we could do that. All right, what about A2? What changes from A1 to A2? If we take a look at how we did this, what changes from A1 to A2? In terms of ideas, if that didn't seem too bad for ideas, then it's not going to get bad. Yeah, instead of doing B0 and S0, we're doing B1 and S1. Otherwise, it stays exactly the same. 0.8, 0.1, 0.2, 0.9, but instead of B0 and S0, that's B1 and S1. In other words, it's times A1. Except we know what A1 is. What's A1? Or maybe more specifically, how can we write this as something times A0? It's the exact same matrix, except how many times have we applied this matrix to go from A0 to A2? Twice. So if I call this thing A, A1 is equal to A times A0. A2 is equal to A times A1. But if we plug that in here, that's A squared times A0. What if we found A3? What do you think A3 is going to equal? A3 times A0. So to go from 1 month to the next month, we multiply by A. So if we're going from the 0th month, the starting, to 3 months, we multiply by A3 times. If we want it after 1 year, A12. What's that going to be? Right. It's A to the power of 12. And after a long time, we just keep multiplying by A. In other words, to go from 1 month to another month, we're just raising the power of A. So at least I've hopefully given you an application to see why we might want to take some powers of A. All right, so if you tuned out because I said, hey, you don't need to know this, tune back in, because now we're going to actually find A to the power of n. So we're going to compute A to the power of n. So 0.8, 0.1, 0.2, 0.9 to the power of n. And this is a learning outcome for this class that we expected to be able to do, is to find this using diagonalization to find this. All right, so feel free to ignore everything apart from this example until now, but here now we're actually getting to a question from this course. All right, that being said, before I jump to that, any questions about what we've done so far? All right, so now we're going to diagonalize. It is a 2 by 2 matrix. There's some scary looking decimals in there, but it doesn't change what we do. What's our first step in diagonalizing? eigenvalues. Now, as we know, not everything can be diagonalized. However, most of the time it can, so very rarely is this going to be a problem. A negative 0.01? Yeah? Did I mess something up? Lambda I minus A? Yeah, okay. Scared me there. All right, so we do this. And if we can factor, again, it's a little harder with the annoying parts of working with decimals, but I mean, it is still just solving. So we get two different eigenvalues, which means that we know we won't have a diagonalization problem. What does it say after lambda squared? Lambda squared minus 1.7. Yeah. We get different eigenvalues. So if there's no multiplicity, although technically multiplicity 1, if everything has multiplicity 1, in other words, they're all different, then we never have a diagonalizing problem. So that's good to know. All right, so lambda equals 1. Shove that into our matrix. What is that? Negative 0.2. That's wrong. Plug in lambda equals 1. Someone's got to program the computer. 0.2, negative 0.1, negative 0.2, and 0.1. We plug it in, and then we just row reduce. So in this step here, for all these things, again, some ugly decimals, but all the same stuff we talked about in our last three examples about how to diagonalize. So row, what's that? Row 1, I guess, equals 5 row 1. That 1, negative 0.5, negative 0.2, and 0.1. And then row 2 is row 2 plus 0.2 row 1. We get 1, negative 0.5, 0, 0. Always get a row of zeros. So x2 is equal to t. And x1 is equal to 0.5t. So what's, again, we're diagonalizing, so we don't need all the eigenvectors. Sure, we could have done that right from the beginning. As always, there's more than one row operation or series of row operations that get the job done. So we could have done row 2 plus row 1 right from the start. Since this is diagonalizing, we don't actually need the eigenspace. So what is one eigenvector that we can use? Because we just need one to create P. Okay, actually it'd be the other way around. But if we wanted to avoid decimals slash fractions, what could we do? Yeah, we could actually let t equal 2 and get the vector 2, 1. But, I mean, if you wanted to, you could have 1. Oh, sorry, the other way around. Other way around. 1, 2. But if you really wanted to, you could have 0.5 and 1. I mean, there's nothing wrong with decimals. They would certainly work. All right, so we got our one eigenvector. That gives us our first thing of P. Lambda equals 0.7. Plug that in, we get negative 0.1, negative 0.1, negative 0.2, negative 0.2, 0, 0. So row 1 divided by negative 0.1, row 2 plus 0.2 row 1, and we get 1, 1, 0, 0. So again, I'm going fairly quickly through the row reduction. That's, that's 3 months ago. And so we get what x2 equals t, x1 equals negative t. So again, just what would be one eigenvector we could use. And since we're going to use this in calculations, let's try and keep it as simple as possible. Yeah, t equals 1 gives us negative 1, 1. In other words, A is equal to P d P inverse. We stick our vectors into P, so that's 1, 2, negative 1, 1. What's D? Right, lambda 1 and lambda 2 in whatever order we did them. And as always, if we did the eigenvalues in the other order, it's perfectly fine to swap these, as long as you realize these would swap as well. The order doesn't matter. Being consistent with it does. And the last one is just the inverse, which usually requires some calculation, but this is a 2 by 2, so we have our adjoint formula right here. Great. So we've managed to diagonalize A. So another example of that. Any questions about how we diagonalized A? All right, so what were we really looking for? Back to the application, we were trying to find AN. So that's going to be A to the N times A0. In other words, so other than the fact that I didn't plug in A0, what's wrong with what I wrote down? Yeah, it would be D raised to the power of N. Right here. So in other words, we get the 1/3, as always, constants can be factored out. And we get 1 to the N, 0, 0.7 to the N, because diagonal matrices are awesome. And now we have some matrix calculations that would find AN, so we would know how many customers each of them have, provided that no circumstances have changed, how many customers each of the companies would have after N months. And I'll blast through these calculations because that's not really the purpose. The purpose here is how we did the powers. So any questions about how we did this before I just knock off the rest of the annoying calculations? All right, multiplying the last two again. Matrix multiplication is associative, so you could multiply the first two together. The last two doesn't really matter. What's that? Negative 1,000. Here we would get, what's that? 2,000 and negative 1,000 times 0.7 to the n. So that's 2,000 plus 1,000, 0.5 to the n, and then 4,000 minus 1,000, 0.7 to the n. So Bn would be 2,000 over 3 plus 1,000 over 3, 0.7 to the n. And Shaw's would be the second one. Right, so again, I don't want you to focus too much on the application, more so on just how we got these matrices and stuff like that. But we did manage to finish off the application, so Bell gets this crazy looking amount after n months, and SN has this other crazy amount after n months. So any questions about, again, really the how we did the power stuff, how we diagonalize stuff? That's the part I want you to focus on. But if you have any questions about the application as well, feel free to ask that. All right, so this is really not a learning outcome in this class. But for those calculus students in this room, for the calculus students in this room, how do we find out how many customers each would have after a very, very long time? Yeah. So after a long time, for those of you with calculus, that's going to be the limit as n goes to infinity of the vector an. So this is just a constant. What happens to 0.7 to the n if n gets really, really big? Yeah, if you take 0.7 and you raise it to a large power, you multiply it by itself over and over and over and over again, well, eventually it becomes so small that it's nothing. Oh, no, the plateau would just be as n goes to infinity. So the 0.7 to the n goes to 0. Don't need any more calculus than that. Limits are good enough here. All right, anyway, you don't for this class, you definitely don't need to know this limit stuff here at the end. Feel free to go take some calculus and learn a little bit more about that. But again, in this class, I want to stress that while I tried to give you the application just so you could give some context of how this might get used, what I really want you to know is, given the matrix, how can we diagonalize it, and how can we use the diagonalization to find large powers, as we did here. And for your own curiosity, there's another question in the slides that gives a different context, just because when I made the slides, I didn't know how much time we would have. So in lieu of time, I'm going to cut it off there. So any questions about diagonalization or any of that before I just open it up to general stuff? All right. So I want to take the remaining time today. You don't need to know about how this can be used to model, I don't know, telecom companies or companies in general. That you don't need to know, but I could have just as easily said, A is the matrix, find A to the n. That I could have said and would have been fair game. So if I give you the matrix and ask you to raise it to a large power, that I do want you to know how we got the matrix from the application. That is optional. All right, so I'm going to open it up to final exam stuff. If you have any math questions you'd like me or to clarify, to go over that kind of stuff, or if you have any questions about the final exam, keeping in mind I can't really answer questions like, how many questions there are, because we haven't made up the test yet, but just general questions about the exam, I'd be more than happy to take the time now to talk about that. Spend the last 25 minutes or so talking about whatever you want to talk about. I will have office hours next week. They're not up on the appointment bookings yet. That being said, Monday, Tuesday, Wednesday. Monday I should have a little, but Tuesday and Wednesday I should have quite a bit of office hours popped up throughout the day. And I'll probably put a small amount, but if they get filled up, I'll probably add more. I used to do it where I put like 10 hours of office hours, but that was when I was in person. So if only 3 people showed up, I could still work all day. So it's a little harder with the appointment bookings. All that linear transformation stuff wasn't challenging? All right, cool. Of course, as always, you can always email me. Absolutely. In terms of the logistical part of the exam, just to let you know, the registrar's office did put 3 hours there. The idea behind that is because I messed up with the midterm and I told them 1 hour, and then they told me later, well, that needs to cover the uploading stuff too. I didn't want to make that same mistake with the final exam. So the final exam is 2 hours of writing, but there is going to be some time ahead of time. All these exact timings is on the course outline, as it always would be. So the 3 hour time takes some sign-in time at the beginning, 2 hours to write, and then time for uploading afterwards. So it is a 2 hour exam, even though the registrar's office will say 3 hours, because the 3 hours will include uploading time, sign-in time, stuff like that. So it's really more like 2 hours and 40 minutes, but 2 hours for the writing time. Linear Algebra 2 is kind of a continuation of some of these ideas. So we talked about Rn as our set of objects we really focused on in this course. Linear Algebra 2, a vast majority of it would be taking a lot of the stuff that we did here and saying, well, what if we wanted to do it with polynomials? What if we wanted to do it with matrices instead of vectors? What if we wanted to do it with functions? And the kind of stuff that we could stays the same, the kind of stuff that's different, how we can work with it and stuff like that. So instead of working with Rn, we're going to take another set of objects and do a lot of the same operations. And that honestly takes up the bulk of Linear Algebra 2, as I taught that this term. So. But it does tend to get more theoretical, the Linear Algebra 2, because in order to do a lot of that stuff, you need some more theory. And as always with the second year math class, there's more theory involved, as it should, the further along you go. Is it possible to see reflections, projections on a line at an angle through the origin? So yeah. So reflections is more complicated. Projections we definitely did. Because all you need is, if all you had was the angle, then you could get the slope. Once you have the slope, you can find a vector in that direction, and that's all you need for a projection. For reflections, we did the example of y equals x. You could do it with more complicated things, but that really wasn't our focus. Why is 1300 a prereq for Math 2720? 2720 is multivariable calculus, and as soon as you go beyond 2 dimensions, you have to start talking about vectors. In 2 dimensions, the only vectors for calculus is the x direction and the y direction. When you get to 3 dimensions, you can start talking about vectors in all different directions. And so it's hard to do the calculus on that stuff without having a good sense of what vectors are doing, which is why linear algebra is a prereq for multivariable calculus. Can I do 4.9, number 25? Absolutely. An actual math question. I love it. $25, $25, $25. All right, for those of you who don't have the textbook on you, this is section 4.9, number 25. Not 2.5, but 25. So it's the orthogonal projection. All right, so first of all, the instructions say find a standard matrix and then use the standard matrix. So it's the orthogonal projection, which really all of our projections are orthogonal projections. So I've just been using projections, but anytime we say projection, it's always orthogonal. Of the point 4.9, of the point slash vector 3, 4 onto the line that makes angle, and it's the line through the origin, that makes the angle theta equals either pi by 3 or 60 degrees, whether you live in radian land. or degree land. All right. So in other words, in terms of, I just put it away. Sure, I can do 27 afterwards. I'm assuming. All right, so we have, what's this, 1, 2, 3 in terms of the general idea. 1, 2, 3, 1, 2, 3, 4. So here's our point slash vector. Call that V, I guess. And here is our line. So we want to use kind of the standard matrix to find out. So the final answer is going to be the vector I'm about to draw in blue. That being said, just want to get used to find our standard matrix first. So let's pretend this was xy, not specifically 3, 4 just yet. And let's find xy. So we just want to find our projection. So if this was a vector u, so call this u, call this v. If we wanted to find the projection of v onto u, how do we do that? So how do we find the projection of v onto u? We have a rule for that. Okay. But we've done this in chapter 3. We already figured out all the ideas. So how do we find the projection of v onto u? What's our kind of formula for that? Fair enough. Fair enough. It's the dot product-y thing over the other, over the length squared thing times u. Fair enough. Too hard to write in the chat. All right, so really, v is xy. So all we really need to do is find a vector u. So that's really the only complicated part of this question beyond just how do we deal with projections, but that's chapter 3, is how do we find u? Because we're given a line. Actually, we're not even given the line, we're just given the angle that it makes. So we're given an angle that it makes. We're given this angle is 60 degrees. So how can we use that to find a vector u? And I'm not saying the, because obviously the length could be many different things. The direction's the only thing that matters. It's just trigonometry. We're talking about the angle between. So we can just use trig. So if u was equal to u1, u2, sure, we could take row 1, or sorry, we could take 1, 0 and rotate it by 60 degrees. Sure. That's one way to do it. It wasn't actually what I was thinking, but that would certainly work. Right. So u1, u2 can be 1, 0 rotated 60 degrees, which is just cosine 60 and sine 60. Root 3 over 2, 1 over 2. And that is certainly one way to do it. Absolutely. Alternatively, we could find the slope of that line. How could we find the slope of that line? If x is cosine and y is sine, how could we find the slope? Not slope. That would be u2 over u1. And how do we find the slope? Yeah, that's tan theta. In other words, the line is y equals root 3x. And we could get, like we did in our y equals x example, we could get a vector that way. So there's a few different ways we can actually find this vector. And the point being is that it doesn't actually matter how we find the vector. We just need one vector. And then everything else is chapter 3, where we just slam it into our projection formula. But I kind of like the rotate 101 because it takes into account other things that we've seen in this section as well. So we can take 10 and rotate it 60 degrees. And honestly, in general, that's what we could do. So if you like formulas, you're about to be happy. So for any theta, we could get u is equal to cos theta sine theta. And then get v dotted with u and all that kind of stuff. Okay. Does it? Okay. Sure. It's in the text. It's fair game. All right, so that's xy dotted with root 3 over 2, 1 over 2, all over the length of root 3 over 2, 1 over 2. That being said, while the formula will do the job, we actually already know what the length of this vector was. But just in case we forget, we can find our length. What did I do? Oh my goodness. Made myself out to be a fool. What else is new? Trigonometry fail. Of course, cos of 60 is a half. Thank you. My tan was fine, though. Somehow I managed to do cosine and sine wrong, but get tan right. Thank you. What are you talking about? It didn't say 60 degrees. It said 30 degrees. All right, so this would be 1/2 squared, so that's a quarter. Root 3 over 2 squared is 3 over 4, so that's equal to 1. So in other words, our projection is 1/2 x plus root 3 over 2y times the vector 1/2 root 3 over 2. In other words, that's 1/4 x plus root 3 over 2 over 4y and root 3 over 4 x plus 3 over 4y. And our standard matrix T is just our coefficients. So that's 1/4 root 3 over 4, root 3 over 4, and 3 over 4. And so T of whatever the original question was, 3, 4, would be all this stuff multiplied. So 3 over 4 plus root 3, 3 root 3 over 4 plus 3. But the point being is that if we are dealing with a projection, the question, like if we're dealing with a projection, this is how we could project it onto the line. So it's really a chapter 3 question. The only real difference here is that we had to find the vector u, but that's just high school trig. So really, this is just a projection question from chapter 3 in the context of a linear transformation. Just like we did in class, a slightly different way of finding the vector u, but just the same way we did in our y equals x projection example from class. Any questions about this example? I don't see why not. All right, somebody asked about 27. So in reality, so for a reflection, a lot of the same ideas work. So this is number 27, same section. So if we're dealing with a reflection, the ideas are still the same, still 60 degrees, 60 degrees. The difference here, of course, is that we don't have a formula like the projection, so we're going to use our standard ideas, find our standard vectors, and work with it. So what happens, now this is reflecting, so if we take 1, 0, so we're finding t of 1, 0. If we take t of 1, 0, and we reflect it about this line, where does it go? So this was certainly, if it was 45 degrees, it would, but not for 60. And this is how we handled, so if we didn't have a nice formula for our transformation, then we just found what it did for our standard vectors. So where does the vector 1, 0 go if you reflected it about something that was 60 degrees? Yeah, it would go shooting off in this direction, where this here is also 60 degrees. So here's t of 1, 0. In other words, what do we get? What's t of 1, 0? Honestly, using our rotation ideas. Yeah. So t of 1, 0 is basically just rotate by 120 degrees. So cos 120, sine 120. Maybe I'll actually get it right this time. That's going to be negative a half root 3 over 2. And we could do the same thing with t of 1 or t of 0, 1. There's 60. Here's 0, 1. Where's t of 0, 1 going to go? Nope. Not the fourth quadrant. Again, the idea is this angle here has to match that angle there. So what's the angle that I've kind of double arced? So this is 30. This is 30. More importantly, what's that angle? Yeah, this one's also 30. And that's the important angle, as we know. So this would be cosine of 30, sine of 30. Now I'm going to get it right. Root 3 over 2 and 1 over 2. So in other words, standard matrix T is negative a half root 3 over 2, root 3 over 2, positive a half. And you could find, once you get the standard matrix, you could multiply it by anything to get the actual answer to the question. Which I think was what happens to 3, 4. So T of 3, 4 would be this times 3, 4, which is negative 3 over 2 plus 2 root 3, and 3 root 3 over 2 plus 2. That probably wasn't the hardest part. So before I get to that next question, any questions about this one? Sorry, for this question or the answer to the question somebody said in the chat? Okay. Yeah, for a reflection, this will not just be what a rotation will be. So no, that wouldn't work, just to use the rotation matrix, because the angle that we needed to get the first vector and the angle we needed to get the second vector weren't the same. All right, so some questions about where these angles came from. Great questions. The point is in order to get a reflection, so this is kind of a general thing. In order to get a reflection, if let's say I had some vector here and some line of reflection, then the output, what we're getting here, this angle and this angle need to be the same. Just think of it as a mirror. If you had a mirror, the angle you got over here would just get reflected on the other side of the mirror. So those angles are the same. So in our first example, we found the angle. So blue is the line we're rotating about. We're told that makes an angle of 60. That's part of the question. So this 60 is part of the question. That would need to be said in the question in order to get this 60. So that 60 was a given. Once we have that 60, well, for 1, 0, this angle is 60. So this angle has to be 60 after the rotation. So put that whole thing together, and the angle we want is 120 degrees. That's probably the one that makes the most sense. I'm not saying it makes sense, but the most sense of the two. So that's 120 degrees. Hence the cos 120, sine 120. For the second one, again, we were given that this is 60 degrees. That was given in the question. So if this angle is 60 degrees, what's the angle between the vector 0, 1 and the line? So we're trying to reflect 0, 1. So what's the angle between that vector and the line? What's this angle right here? So that would be 30. 90 minus 60. So we're getting our 30 right here. So that's 30 degrees. So when we reflect the vector over here, here's t of 1, 0. When we reflect, this 30, and this has to match that 30. So that's why T01 points in the direction that it points. However, if we want to use cos theta sine theta, the real angle we need, just like up here, the angle's got the formula, the angle's got to start at the positive x-axis. That's just what trigonometry does. Then we need to know this angle. So if we're going to use, cos theta sine theta, we need to know this angle theta right here. And so in this case, well, again, this whole thing's 90 minus 30 minus 30. So it happened to be that theta equals to 30. And hence, that's where the 30 degrees came from that went into the formula. What if the angle of the vector isn't so nice? Then you would leave your answer as cosine of 47 degrees, and that's where you'd leave your answer. If it's not one of our 30, 45, 60, 90, 0 variants, then we would just leave it like this. You obviously don't have a calculator. All right, I wanted to get to somebody's question from earlier on. That seemed to be different. So what if you wanted to rotate by 60 degrees in the clockwise direction? So was that just a rotation question? What if you wanted to rotate by 60 degrees in the clockwise direction? Like if it was just a rotation? In this question, okay, so in this question right here, if we wanted to do 60 degrees in the opposite direction, our ideas would still say the same. So if this was 60 degrees, so T of 1, 0 would still end up over here. So that would be cosine of negative 120 degrees, sine of negative 120 degrees, just as it was before. As for the other one, if we had T, or if we had 0, 1, that'd be a little bit more complicated because what would this angle be? If this one is 60, what's the angle from the vector to the line? So that's 150, which means when we reflect it, and honestly, I should make sure this line just keeps going. If we reflect it, really, we're going to add another 150 degrees to this and end up over here. Quite honestly, it's just, if we wanted to go clockwise 60 or counterclockwise 60, because it is a line going in both directions, we're technically just going counterclockwise 120. But either way, we get 60 here, 150 here, so our angle, theta, would be negative 210. The original 60 plus the extra 150, we get negative 210, which honestly is the same thing as 150 degrees. But either way, we get T of 1, 0 is equal to cosine of negative 210, sine of negative 210, which would be whatever it is. So kind of like with rotations, we're keeping the same ideas, but the angle is negative. Oh. For reflecting 0, 1 through a line that is an angle 60 to the x-axis, it kind of looks like rotating 0, 1 by 60 degrees in the clockwise direction. Yeah, sure, fair enough. Fair enough. So in theory, you could come up with a formula that would say, all right, start at 90 degrees and then subtract 2 theta. If we're looking for a specific formula. That's not exactly right. Technically, it's subtracting. Yeah, that's not 100% right. Technically, it's 2 times 90 minus theta. You just have to be a little bit more careful with it. Alrighty, well, I'm already 5 minutes past time, so I guess that's it. Good luck to you in all your exams. Have a good rest of your year.